Hello, my name is Rob Reynolds. Welcome to mat-073. Today we're on section 6.4 and we're going to be looking at how to add and subtract radicals and combine like terms. So again, just like if you had x plus y, I cannot combine those. So if you have the square root of 2 plus the square root of 3, you cannot combine those. The only thing you can combine the square root of 2 with is maybe 4 more square roots of 2 for a total of 5 square roots of 2. So we're going to treat the square root of 2 like a variable, like it's an unknown variable, x. And you can only combine x's with other x's. So I'd like for you to look at this problem. 3 square roots of 5 plus 7 square roots of 5. Treat it just like 3x plus 7x for a total of 10x's, or in this case, 10 square roots of 5. So if it has the same cube roots, I'll just say of a box. So 7 boxes plus another box, take away 2 boxes. Or you could think about those all being x's. Gives you 6 of those boxes, or 6 of those x's, or 6 of those like terms. So the author agrees 10 square roots of 5 and 6 cube roots of 9s squares. If they don't have the same box or the same x, then maybe we could simplify the square root of 18 to be in terms of the square root of 2. So let's see if we can break down the square root of 18 as the square root of 9 times the square root of 2. And the square root of 9 is 3. So this is really 6 square roots of 2. Take away 7 square roots of 2, which is negative 1 square roots of 2. Likewise over here, maybe we could simplify so we can get the same like terms to combine. So I'll break this up, the cube root of 24 and the cube root of m cubed, because we remember a rule that said the square root of ab is really equal to the square root of a times the square root of b. Same works for cube roots. And the cube root of m cubed is just m. 24 can be broken up into the cube root of 8 and the cube root of 3. So just like we have perfect squares memorized, I would start perfect cubes. So 1 is a perfect cube, but it's not very useful. 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64, and 5 cubed is 125. So I would at least memorize perfect cubes up to 125. So you can work on simplifying cubes, and you can see that 24 can be broken down into picking a perfect cube of 8. So the cube root of 8 is 2, and I'm going to bring the m out front. So pronounce this 2m cube roots of 3. So now I've got 10 cube roots of 3m. So if this term would have been a 4, which is what I think the author originally intended this to be, then this would be the cube root of m cubed, and the cube root of another m is around here somewhere. So this is the cube root of m, and we have another cube root of m here. So this is 2m cube roots of 3m and 10 cube roots of 3m. Still doesn't have like terms. I think the author here probably meant for there to be an m right here. So I think there's 2 mistakes here. I think this is probably meant to be a 10m. And the reason why is because I had to get this box to look just like this box. So now each box contains m cube roots of 3m and m cube roots of 3m. If those boxes aren't the same, and the author didn't intend this to be the problem, then I couldn't combine these. But I really do think the point of this problem was to be 12 boxes, which is m cube roots of 3m. You can see on the next slide, he does add this m here, and he changes this m cubed to an m to the 4th. So I apologize about that problem. You can see that was not the original problem, but they had changed it so that they would have like terms in order to combine. So instead of adding or subtracting, next we're going to look at how to multiply radical expressions together. We can distribute just like we did for integers. So this will be y square roots of 2, and I suppose you could write that as the square root of 2y, but then I get a little bit nervous if that radical sign is over the y or not. So I would prefer, so that there's no confusion, to put everything that's not underneath the radical in front. And we know that the square root of ab can be broken up into the square root of a times the square root of b, but we could also go backwards. The square root of 2 times the square root of 7 can be the square root of 14, and sometimes I can even simplify that, but there's no perfect square that goes into 14, because perfect squares are like 2 times 2 is 4, 9, 16, and 25, and none of those numbers go into 14. So I believe this would be the final solution, and it looks like the author agrees. Here you're actually going to use the FOIL method because it's a binomial times a binomial. So first terms, the cube root of a times the cube root of b is really the cube root of x times x squared, which you should probably know as x cubed, and the cube root of x cubed is just x. So that's just the first term. The outer terms is going to be minus 3 cube roots of x. The inner terms is plus 2 cube roots of x squareds. And then the last term is going to be minus 6. And honestly, this looks like it might be able to be combined, but remember, we don't have the same term. This is the cube root of x, and this is the cube root of x squared. You can multiply those terms together, but you cannot add those terms. They have to be identical in order to add them. So I think we're done with this problem. You cannot combine the first, outer, inner, or last. The last example says the square root of m times the square root of m, which is the square root of m squared, which I would just write as m. Outer terms is minus the square root of mn. The inner terms is positive. Now you could either write n times m, which is the same thing as m times n. So 4 times 5 is the same thing as 5 times 4. The last term is a positive times a negative, which is going to be a negative term. And the square root of n squared, which again you should know as negative n or minus n. I think these middle terms will cancel. I've got negative mn and a positive mn. So I think all of that just drops out to be a 0. And the final answer is m minus n. So it's really called the conjugate when these outer and inner terms cancel, or when you literally change that middle sign from a positive to a negative or a negative to a positive. It's called the conjugate, changing that middle sign. So sometimes that's a nice strategy to help simplify. If you have a binomial squared, you do not have the conjugate because you haven't changed the middle sign. This literally means multiply by itself. 5 squared means 5 times 5, which of course is 25, but it literally means multiply by itself. So if you were to multiply 3 square roots of 6 times 3 square roots of 6, that's 9 square roots of 36, which is really 9 times 6, which can be simplified to 54. The outer terms is 2 times 3, which is positive 6 square roots of 6. The inner terms is another 6 square roots of 6. And the last terms is 2 times 2, which is 4. Now these inner and outer terms, this time I have like terms. So 6 square roots of 6 plus 6 square roots of 6 is 12 square roots of 6. And then lastly, I can combine the 54 and the 4. So final answer is 60 plus 12 square roots of 6. Yeah, 54 and 4. How about 58? And 12 square roots of 6. Good, good, good. And the author agrees. I hope you found this video helpful. If you have any questions, feel free to email me.